Welcome to this online revision session for AQA FP2. In this session we're going to cover the January 2010 question 7, which covers series and proof by induction. Right, as you can see in this question, a sequence is defined. Its first term is 2, and then each subsequent term is twice the previous term plus 1. And we have to show, firstly in part A by induction, that the general rule for any particular term is given by 3 times 2 to the n minus 1 minus 1. And then in part B we then have to use the result to help us express the sigma notation result in terms of un plus 1. Well, we know that to do proof by induction we've first got to show that it's true for the first term, and then the second part of the problem is to then show that if it's true for any particular value of n, let's say k, then show that it must also then be true for k plus 1. So we'll start off by letting n equal 1 to begin with. So if we let n equal 1, then we can see that u1 is equal to 3 times 2 to the 0 minus 1, which is equal to 2, which of course is the result that we required because the first term was supposed to be 2. Okay, so it's true for n equals 1. So the next part of our inductive process is to assume true for n equals k. In other words, what we are saying is that uk is equal to 3 times 2 to the k minus 1 minus 1. Now we're going to show that if n equals k plus 1, that also is going to be of the same form using that particular result. Okay, so what we're going to do, right, so we're letting n equals k plus 1, so we're looking at u k plus 1. Now we know from its definition that it's equal to twice u to the k plus 1. Right, this is from the statement up here. Now we know that u to the k, we've just assumed it can be rewritten as 3 times 2 to the k minus 1 minus 1 plus 1. And then if we multiply this out, we're going to have 3 times, well, 2 to the k minus 1 multiplied by 2 becomes 2 to the k. And then we're going to have minus 2 plus 1, which gives us 3 times 2 to the k minus 1. And that is in the correct form because it's in the form of 3 times 2 to the correct form, and to show it's the correct form we could rewrite the top of this as 3 times 2 to the k plus 1 minus 1 minus 1, to reiterate the fact, yes, this is in the right form here. Okay, and so we can say therefore that it's true for n equals k plus 1. And then we can say, by induction, un equals 3 times 2 to the n minus 1 minus 1. Okay, so where are we getting our 5 marks? Well, for showing our result for when n is equal to 1, that will give us 1 mark. Then, assuming it's true for n equals k, and then letting n equal k plus 1, that is going to give us a method mark for showing that we understand the inductive process that we're going to use, the assumptions that we need to make, and writing down an appropriate statement that is accurate at that point. And then simplifying it down to 3 times 2 to the k minus 1 will get us a mark there. And then finally, for showing that we understand the inductive process and making a statement appropriately, will give us a mark to finish off with. Okay, so that gives us our 5 marks for that part of the question. Okay, now moving on then to part B. Alright, remembering we just shown the result that's true for our sequence. We've now got to find the sum of all of our terms. So we know then that the sum from r equals 1 up to n of ur is equal to, well, each term ur we have just shown is equal to 3 times 2 to the r minus 1 minus 1. And so we can split that up and separate it into well, what can we separate it into? And so we can see that we can split this up. We're taking out our factor of 3, and then we got the sum from r from 1 to n of 2 to the r minus 1 minus, and then the 1 of course is subtracted from each of the n terms, so this becomes minus n here. Well, what we need to now notice is that this part here is a GP, because if I wrote it out longhand, when I put r as 1 in, I'd get 2 to the 0, which is 1. I put r as 2 in, I get 2 to the 1, which is 2. And r as 3 in, we'd get r squared, which is 4. And so it's the sum of 1 plus 2 plus 4 plus 8 and so on, up to 2 to the n minus 1. Okay, now that GP, we should know that the sum of it is 1 minus r on the bottom, or r minus 1 since r is bigger than 1. So we get 2 minus 1, and on the top this is going to become 2 to the n minus 1, and so we just end up with this being equal to 2 to the n minus 1. So this is from your knowledge of GPs. And so now we've got 3 lots of 2 to the n minus 1 minus n. Now, can we relate that back? Well, we should be able to, because if you remember, the term un is equal to 3 times 2 to the n minus 1. So if this is 2 to the n, then this must be the same as 3 times 2 to the n minus 1. But of course from that bracket you had 3 times minus 1, which was minus 3, so we've got to subtract another 2. So if I collect that together with this n here, this becomes n plus 2. Okay, so you need to satisfy yourself there. You can see what I've done with multiplying out the bracket and splitting the minus 1 and putting the 2 with the n, because now this term here is now equal to u n plus 1. And so I've got the result that I required. Okay, a little bit tricky on the algebraic manipulation, and of course the key thing was realizing that this summation here, the sum from r equals 1 to n of 2 to the r minus 1, is a GP, and we needed to sort out the summation of that GP. Well, 3 marks. We'll get a method mark for appropriately expanding and simplifying this term, 1 for getting an accuracy mark up to this point, and then 1 mark for getting through to the required result. Okay, right, well, hopefully you found this question useful. For further help and support, please go to the Further Maths Support Programme website.